We are now going to try one of our speed sessions. We have 3 presenters here, and we're excited to hear from them. So let's hear from our first presenter. Sharon, the floor is yours.
Sorry. Hi, everyone. I'm Sharon Ayayo, and thank you so much for giving me opportunity to present my study, which is titled "The Drivers of One-Year Mortality Decline After Acute Myocardial Infarction in England and Wales." Next. So AMI is a leading cause of mortality in the world, and in the UK alone, there are about 100,000 hospitalizations and about 20% of those resulting to death. The aim of our study was to examine the mortality changes over time and its determinants in people with AMI or heart attack. So we used the data from the Myocardial Ischemia National Audit Project, which was linked with the Hospital Episode Statistics and Office for National Statistics. So MyNAP database is a national registry in the UK where all AMI admissions are recorded, and ACE records all admissions, both MI and non-MI, and ONS is a mortality registry. So our study population included just over 852,000 AMI patients. Our primary outcome was all-cause mortality at 1 year, and this diagram here just shows a group of how we grouped our 34 covariates into 10 clinically meaningful groups. For example, demographics, age, add variables like age, sex, ethnicity, and so on, where we use this fairly decomposition method to quantify the determinants of mortality changes between 2 years. Next. So these figures show how mortality have changed over time. The first one is overall mortality. There was a reduction. And then the next one is by AMI subtypes. So the blue line is for non-ST elevated myocardial infarction, which was a higher mortality than the STEMI, and mortality reduced for both. The next one is by sex. So female had higher mortality than males. That's the red line at the top, and mortality reduced over time for both. The next one is by age group. The red one at the top is the oldest age category, which was 80 years and above, and they had the highest mortality over time, and there was a slight reduction as well. Next. So next we move to the results of the Fairley decomposition method. So it just quantifies, it tells us by how much percentage each of these covariates contribute to the difference in mortality between 2 groups, can be 2 time periods, or like in our case, or other groups. So there was a difference of 8.6 percentage points between, we used, instead of using single years, we grouped them into 3 year blocks. So that's 2005 to 2007 and 2017 to 2019. So there was a difference of negative 8.6 percentage points. And this table shows the top 3 contributors to the reduction in mortality that was observed. The first one was pharmacology, other groups, with a percentage contribution of 27.7%. So pharmacology had variables like statins, beta blockers, ACE inhibitors. So those are the ones that contributed the most to the reduction in mortality that was observed. This was followed by percutaneous coronary intervention with a percentage contribution of 17.6%. And then demographics came third with 10.6%. And in total, all these variables explained 68.2% of this difference that was observed. So there's still around 30% that remained unexplained, maybe can be from other lifestyle factors that was not captured in our database. So
It's time to wrap
conclude,
up.
so these are the key messages. So there's a reduction in 1 year mortality over time, and this was due to medications like statins, ACE inhibitors, and percutaneous coronary intervention. So the clinical implication is that it shows the importance of pharmacological treatments and PCI in reducing mortality. And for future studies should explore the drivers of the unexplained component of the mortality decline.
Thank you very much, Sharon. And we'll hear from our next speaker, which is Oh, that's Sharon's contact information. Please do reach out to her. And we'll hear now from Wendy Cham. Proceed, Wendy, the floor is yours.
Hey, thank you. Hello, everyone. My name is Wendy Chan, and I'm from the University of Pennsylvania. Thank you for this opportunity to discuss a new project that I've been involved in, which focuses on the generalizability of experimental studies. So to give a brief introduction, generalization refers to the extent to which the results based on a sample of participants apply to a larger population of individuals. And in practice, random sampling is considered the strongest tool to strengthen generalizations. However, random sampling is rarely done in education studies. And as a result, researchers have turned to propensity score-based methods to address the selection bias due to non-random sampling. To date, propensity score methods have been used in post hoc approaches to estimate average treatment effects, such as in matching and reweighting, but they've also been used in study design to assess how similar or generalizable individuals are between the sample and population. Next slide, please. So in practice, 4 statistics have been proposed to assess the generalizability or similarity between a sample and population, with the understanding that if individuals in the sample are similar to people in the population, then the results of the study will be applicable or generalizable to those in the larger population. And we often use 4 statistics to assess this generalizability or similarity, and they are given by the standardized mean difference in propensity scores, the generalizability index or B index, the overlap in propensity score distributions, and the average absolute standardized mean difference in observable covariates. Next slide, please. But in many cases, these 4 generalizability statistics may come to the conclusion that the sample is not similar to the population. And researchers in those situations are then left with a big question, which is if generalizability is still the goal of the study, how can we best improve the extent to which we can generalize? Or where are the differences between the sample and population being associated with? So in this study, my students and I investigated the relationship between a distance measure that is known as the energy distance and those 4 generalizability statistics to see if there is a way to pinpoint the differences between the sample and population. As a summary of this slide, the energy distance is a member of the class of energy statistics, which are measures to quantify the difference in probability distributions, which in our case is between the sample and the population. The formulas on the screen give you the way to compute the energy distance, but it is basically computed using the sums of the Euclidean distances between, in our case, the covariates from the sample and the population. While there are other distance measures that are available, we chose to focus on the energy distance because it is fairly easy to compute. And is also very sensitive to differences in the distribution, which is something that gives it an advantage over other measures that might only focus on the first moment or the second moment. Next slide, please. So my students and I conducted a series of simulation studies to investigate the relationship between the energy distance and those 4 generalizability statistics. And as a summary, one of the things that we found was that there did seem to be a correlation between the energy distance as well as another distance measure, which I did not cover today, the Hellinger distance, and those 4 generalizability statistics. Among the factors in our simulation that we found to be the most predictive of that relationship were the total number of covariates, where the more covariates that we were working with, the more variability that we observed in the energy distance and also the generalizability statistic measures. And that is an important consideration, especially when we're working with high dimensional situations in which the number of covariates that we have far exceeds the number of individuals in our study. Another thing that we found was that these distance measures and their values could be potentially used to identify sources of systematic differences. And we argued that this could be useful in helping to redefine populations of inference to improve generalization.
Thank you, Wendy. That's our time for today. Thank you. We'll hear from our final speaker, Jacquelyn. The floor is yours.
Hi, everyone. I'm Jacquelyn, and I'm going to talk to you for a few minutes today about a potential career path where I think statisticians could thrive, and that is product management. And I've titled this The Accidental Product Management because I'm a product manager and I did not plan to be one. Next slide, please. So a little bit about me, statistician and data scientist. I'm a product manager for longitudinal analytics and insights at WebMD Ignite. And I'm going to define product management while we're on this slide in case anyone wants to take down my contact info. So product management is the strategic process of overseeing a product's entire life cycle from initial concept to eventual retirement, which is very broad and not super helpful. What we do in this type of role is we're responsible for defining a vision and strategy, understanding what our customers need and what the market needs, and leading cross-functional teams to deliver some kind of product on time. And in my case, this is all data products. So this could be a model, this could be reporting, this could be any number of things that involve data. Next slide, please. What type of skills do we need? Understanding your business context is super important. These are some questions that you may want to that you think about a lot. What is the problem we need to solve? What's happening in our current industry? I happen to work in healthcare technology and marketing data science. So I think a lot about what do marketers need to know to do better marketing on behalf of hospitals and insurance companies. Analytical thinking, this is where I think statisticians have a great superpower and can bring a lot to the profession. What types of data sources are available? What types of biases are inherent in them? All kinds of things related to models and algorithms and how their performance changes at the scale of data. I work with billions and billions of rows of data coming from multiple clients every day. There's a lot of cost and benefit trade-offs I have to consider. So there's a lot where maybe it's not the most accurate statistical model that I could build or that we could put out onto the market, but it performs at the cost that we need where someone will buy it at a high enough prediction or well enough. And so we have to consider all of that. It's very broad thinking. And communication. So you're communicating with technical and non-technical stakeholders. In my case, I talk to clients who are marketers at a hospital. I talk to our internal marketers that do things on behalf of hospitals. I talk to data scientists. I talk to data engineers. I talk to software developers. I talk to executives in the business. And I have to intake a lot of information. So listening, very, very important. And I also have to translate all kinds of data outputs in a way that all of those audiences can understand. Next slide, please. So how do I get there? If you're interested in this, this is a field where educational degrees are not as important. In my case, I have a background in engineering and biostatistics. I happen to be working during graduate school. I did research with Alzheimer's disease and rheumatology. I also worked in industry while I was finishing my PhD dissertation as an operations analyst. I was also a product data analyst at a patient education nonprofit, and then stayed there after I graduated. That's where I was working when I graduated, and we were bought. And then when I interviewed with the company that bought us, they were looking for someone with longitudinal data experience. So this is a field that there's no one path to get there. And there's all kinds of industries and all kinds of work situations that hire for this role. So it's one where I think no matter what your background is, you can thrive in it. And whatever industry you're interested in, there are data problems to be solved there. And so if you like communication, you like working in the data or the business of data, it's a very interesting field to be in. Thank you.
Thank you, Jacquelyn. And thank you to all of our speed session presenters. We appreciate you coming and being so quick on your feet. Thank you again.